Hello, dear friends. This is Mechanical Vibration Lecture 5. This is the continuation of previous lecture. In our previous lectures, we tried to cover some important topics. Let me simply recap those important topics before starting today's lecture. So in our previous lecture, we tried to cover the basic introductory part of mechanical vibration, including basic definitions of terms or the terms which are related with vibration. And the second part which we covered is the undamped free vibration. Topics related with undamped free vibration or a free response of vibration. And in the third lecture, we covered the damped vibration or the damped free vibration of single degree of freedom system. So under this topic, we covered the viscous damping condition. So when we talk about damped free vibration or viscous damped case, we have three important cases related to the damping. So on that, regarding the damping factor, zeta, the damping conditions can be classified into three important categories. One is underdamped condition, in which zeta value is less than 1. Critically damped condition, for which zeta is equals to 1, and overdamped condition. So in the case of overdamped, the value of zeta is greater than 1. And the conditions in every underdamped, critically damped, and overdamped conditions are clearly defined in the previous lectures. And also, we covered the logarithmic decrement when viscous damping applied to the structure, the amplitude difference in every cycle. What is the reduction of amplitude from after one complete cycle? That is what we call a logarithmic decrement, which is also covered in our previous lecture. So today we'll continue from that lecture, considering other kind of damping, because it is not only the viscous damping condition. We have to see other also conditions like hysteretic damping, structural damping. So what are these things? Let's see today. Before that, we'll continue with also the recap lecture of this thing, the same topic. So please pay attention for the this lecture. Okay, let me zoom the screen. So in our free response case, this is the response from a simple harmonic motion using angle sensor and easy sense. So this is all the amplitude are the same. This is free vibration condition. Okay, so this graph implies the free vibration, or recap on free vibration case. And this is the resonance condition. So how the resonance happen? This is the point where the natural frequency of the vibrating system and the natural frequency of the material comes to coincide. The point where the amplitude of the vibration will exceed to a very large amount, so, or it can be infinity. So that is the condition of resonance. So this is the point where resonance condition happens. So resonance is characterized by a large amplitude. Okay, so that is the condition of resonance. So In this, we can see the amplitude increases rapidly as the frequency of the driver is the same as that of the driven system. So we have a driven system and driving system. When both of them comes, their frequency coincide, that is what we call resonance occurrence. So this is underdamped vibration case. In the case of underdamped vibration, free vibration decaying over a long period of time. So this is the logarithmic decay of amplitude during underdamped vibration case. So this graph implies, yeah. So how is the effect of damping? Okay, increasing level of damping from here to here, the amplitude of vibration decrease. As damping level increase, the amplitude of vibration decrease. So this may be underdamped condition. And when we come to this, it is maybe damping with very less damping ratio. And this one is damping with higher, high damping ratio, higher and a very higher damping ratio yields this type of response. Okay, so these are. So this is underdamped oscillation case, what we have discussed. This is underdamped oscillation condition. And this is the what we call the logarithmic experiment. So displacement time graph. And when we see this is overdamped case. In the case of overdamped, the oscillation is immediately comes to equilibrium position, maybe before even one complete cycle. So it is very steep, and which approach to this equilibrium position, simply approaching, but does not just go to the equilibrium. So this is the graph of overdamped condition. And this is also the graph of critically damped condition, that zeta value is equals to 1. In the case of zeta is equals to 1, it is goes like this, but will not repeat the vibration, or the repetition is not there in the case of critical damped and overdamped. But this repetition happen only in the case of underdamped vibration case. What are the effects of resonance in the structure? We can simply take some examples to understand the effect of vibration. We already discussed this thing in the first chapter, but let's revise. So the tuner in the radio or television enable us to select the program that you are interested is due to, we can see it here, the tuner in the radio. Okay, so this is the circuit in the tuner is adjusted until resonance is achieved. So at the frequency transmitted by particular stations selected, hence the strong electrical signal is produced. So we know this radio, so we can select frequency in which we can get the appropriate bands. Okay, so another is the loudness of the music. Okay, the loudness of music. This is the musical instrument. So the loudness of the music produced by musical instrument, such as in the case of trumpet and flute, is result of resonance. Another best example, which I already discussed before, is the bridge which collapsed in USA. Okay, this is one of the best example. And the glass cracked because of the singer's song. Here, vocal frequency and the frequency of the glass coincide, which is completely crashed. So the cracking of wine glass is also another best example. So another effects of resonance are the soldiers that marching over the bridge. Okay, the bridge collapsed due to the soldiers marching. So the failure of bridge due to marching of soldiers over the bridge, also one of the best example of resonance condition. Okay, so a driver on a springboard builds up amplitude of oscillations of board by bouncing of its natural frequency. So many examples we can give the condition of resonance. Okay, so the Tacoma Bridge, collapse of the Tacoma Bridge is the one which we have discussed at the very beginning here. This is the collapse of Tacoma Bridge. Okay. Okay, so how we can introduce what you call this viscous damping? That is our question. So as we see here, there is piston cylinder mechanism here. And the piston cylinder mechanism, there is a viscous fluid introduced in between them. Okay, so which acts as a viscous damping for this system, which is called a shock absorber system. Okay, so here also the same condition. Okay, here we can see coil spring, which is for K values. There are a shocker with blue color here, okay, which is there. In every aircraft structure or landing gear, we can observe these mechanisms, because when aircraft comes to land, that it produces a lot of shock. So that shock will not transmit into the structure of the body of aircraft. So this shock absorber systems immediately takes all the shocks and all the bumps or impact on the ground directly to the, it converts it to heat and sound energy. So for that purpose, it is introduced here. This is the landing gear of aircraft. Okay, so how we can plot the underdamped vibration condition. This is the underdamped vibration condition. The oscillation will goes like this with decaying of amplitude. So the decay of amplitude is a factor of this factor which we have derived before. So I request you to refer this part. Yeah, this is what we have discussed already, the resonance condition. Okay, natural frequency here, F0, frequency, forcing frequency. So whenever forcing frequency and natural frequency coincide, that is the point where resonance will occur. So this is the undamped or resonance condition. And this is very small damped case, and this is large damped case, as we have discussed in the previous topic. Yeah, these are the three underdamped condition, critically damped condition, and overdamped condition. The oscillation for underdamped, that is zeta less than 1. The condition for zeta is equals to 1, and the condition zeta greater than 1. This is what. So let's see the amount of energy dissipated during viscous damping condition. So we already discussed the logarithmic decrement in the last lecture. So what is the amount of energy dissipated? So in viscous damping system, the rate of change of energy with time, or dW dt, which is equal to force times velocity, which is equal to C, that is the damping coefficient. No, this is damping value C over dx dt whole square. Dx dt means x dot. x dot square, that is velocity. Okay, so the negative sign in the above equation denotes the energy dissipation with time. Assuming single harmonic motion, the solution of x of t is equals to x sine omega dt for the damped case. This omega d is already we defined, which is equals to omega n times radical of 1 minus zeta square. Okay, we can define that term with, okay, omega d is equals to omega n natural frequency, omega n times radical of 1 minus zeta square. So this is called omega d, where x is the amplitude of motion and the energy dissipated in complete cycle is integrating this dw, we can get c dx square. So that finally gives, after integration, what you can get is this expression. For 0 to t, t means time period for one complete cycle, or damped period. It is td. It should be td because damped period. So that 2 pi over omega d from time t0 to 2 pi over omega d. By integrating this, what you can get? This is the work done in one complete cycle by viscous damping. Pi c omega dx square. This is work done. Here we can substitute some trigonometric correlation, because sine square is equals to 1 over 2 times 1 minus cos 2 theta, and cos square theta is 1 over 2, 1 plus cos 2 theta. So we apply these trigonometries in this equation. Okay, so the trigonometric correlation must be replaced in order to get this. So this is a condition of spring mass spring damper system. Okay, the spring damper system of viscous damped condition, and this is the cycle of energy cycle, that loading and unloading cycle of viscous damped condition. So here we can see this point is CWX, and here we can divide this section into two. One from here to here, KX, that is the part of the spring, and another one is CW x square minus x square. We can drive this, I will show you these points in the next part, so let it be as it. So this shows that the energy dissipated, delta W, is proportional to the square of the amplitude of the motion. As we see from this equation, it is proportional to x squared. It is proportional to omega d. It's proportional to c and the pi. But the k term is not come here. This k term is not included here. Why it is, we'll see that later. Not that it is not constant for a given value of damping and amplitude, since delta W is a function of the damping frequency omega d. So that spring force will do any network over a complete cycle? That is a question. That is what I said. This the spring force is not considered. It is not coming into picture here. Why that the spring part not coming into picture? Let's see. So let's take the balance. The force, total force is equals to minus Cx minus Kx. from the free body diagram. From this free body diagram, when we cut it from here, okay, we have a spring part, we have K part, okay, and there is a system which is subjected to some external force F. Okay, so considering this axis as positive, so F is equal to Cx. This is Kx. This is Kx. This is C times X dot. Okay, so F is equal to minus Cx dot minus Kx. So this is the force. And if we assume simple harmonic motion as a solution for this, then x of t is equals to x sine omega dt. Then x dot t is equals to omega d x cos, because once we differentiate this one, what we can get is x dot. So let's substitute this term and this term into the equation. So F is equals to minus CWD x cos omega dt plus minus kx sine omega dt. This is F. Now, work done is equals to W is equals to integral of F times x dt. Okay. From this relation, from this from this relation, dw is equals to, dw dt is equal to F times velocity. This is F x dot. Okay, so dw is equals to F x dot dt. Okay, so this is the relation which we include there. So yeah, here dw is equals to F times x dot dt. So this part is about all about that. So F is already defined. This is the F terms, okay, and x dot is this term. This is completely F. This is x dot. Okay, so this is dt in terms of omega dt. Okay. So from this we compute just multiplying this term with this and with this. Finally, we can get this one. And then we have also here some trigonometric correlations that must be applied to this formula. Okay, this is like this. Here also we can put like this. Okay. So finally, what we can get is c pi omega d x squared plus 0. This part, if we substitute the values of 0 to 2 pi omega d in this equation, what we can get is 0. Because cos 2 pi omega dt in the place of t, if I substitute 2 pi omega d, it gives the same thing. And also if I substitute 0 also, we can get the same, because that is cos of 2 pi is 1 and cos of 0 is also 1. So 1 minus 1 is 0. So this part will eradicate from the our calculation. So it is 0. So finally we can get the same answer. So that shows the spring force will not do any network over a complete cycle or any integral number of cycles. Okay, that is the answer. The fraction of total energy dissipated in each cycle of motion. So we can also compute the fraction of total energy of the vibrating system that is dissipated in each cycle of motion, delta W over W. So the total energy of the system W can be expressed either in the maximum potential energy, that is half kx square, or maximum kinetic energy, half mv square, that mv max square. So which is equals to half m omega d square x square. V maximum is omega d x square. V max is equals to omega d times x. X is the amplitude of the maximum amplitude of vibration. Substituting it, we can get this. So delta W over W is equals to pi CWD x square over half mv square, which is equals to pi c omega dx square over half m omega dx square, which is equal to 2 pi c over m omega d. So by rearranging some terms, this is equals to delta W over W, or the ratio of energy dissipated to the total energy is equals to 2 times 2 pi omega d dot times c over 2m. This means 2 delta. This term is the delta term, that is logarithmic decrement in our previous discussion, and which delta is equals to 2 pi zeta. Again, delta is equals to 2 pi zeta. So which is equal to 4 pi zeta is the ratio of delta W over W, which is equals to 4 pi zeta. So the quantity delta W over W is called specific damping capacity. The ratio of dissipated energy, or the ratio of dissipated work done, or the total work done, is known as specific damping, and useful in comparing the damping capacity of the engineering material. Another quantity known as the loss coefficient, which is also used for comparing the damping capacity of engineering material. The loss coefficient is defined as the ratio of energy dissipated per radian and the total strain energy. So which is equal to, loss coefficient is equal to delta W over 2 pi W. Means it is delta W over W divided by 2 pi. So delta over 2 pi, which is equals to 2 zeta. So this is the loss coefficient. So this is all about viscous damping condition. So we'll continue for other damping conditions. So let's see Coulomb damping condition. But before Coulomb damping condition, if any confusion in this, I don't know. I try to clarify it clearly in stepwise. But if any question, someone can send a message. Okay. So let me continue. Free vibration with Coulomb damping. So here the situation is different from the previous one. In the case of viscous damping, we consider a viscous fluid. Okay? We consider a viscous fluid, and the friction between sliding surface considered 0, which is frictionless. But in the current case, the friction between sliding object and the surface is not 0. There is some frictional value. Mu is equals to, mu is different from 0 in this case. Okay, so this is the condition of this. Free vibration with viscous damping case, this friction surface here is considered 0. Mu is equals to 0 in this case. But this case, mu is different from 0. It is having a value of some different from 0. So here we consider that the friction force. And from the concept of statics, friction force is equals to mu times normal. Normal means the weight acting on the structure is normal. If there is no other force, only the weight of object is acting on the surface, then weight is considered as weight and the normal to the weight are equal, so that force of friction is equals to mu times the weight, mg. Weight is mg. Okay, this is the case. Okay. So in vibrating structure, whenever the components slide relative to each other, dry friction damping appears internally. As stated, Coulomb damping arises when the body slides on dry surface. Coulomb law of dry friction states that when two bodies are contact, the force required to produce sliding is proportional to the normal force acting on the plane of contact. Therefore, the force F is given by mu n, and this n is equals to weight. Okay, so that is mu mg is the frictional force, where n is the normal, w is the weight. Okay. So Coulomb damping, in Coulomb damping, sometimes called constant damping, we call. So since the damping force is independent of the displacement and the velocity, it depends on the normal force that acting over the surface. Since the friction force varies with direction of velocity, if we apply force to the right, the friction is to the left, while it is opposing the direction of the motion. And when force is applied to the left, the friction force is towards to the right. So that is the law of action and reaction. So from Newton's law of action and reaction, whenever some action force applied, there is an equal and opposite magnitude reaction force. That is the logic behind of. Okay, so mx dot is equals to minus kx mu n. Actually, we have the same equation in. We cannot easily get the same equation in both directions. If I apply for move the object to the right, that is different, and when I move the object to the left, that also different. So different equations appear in this case. So what we can do, we can see those things later. Anyways, okay. So let's consider case 1. When x is positive and x over dt is positive, that means when both of actually the object is moving towards to right, from left to right. Okay. Instead of this, we can say when an object moves from left to right with constant motion. Then what the equation seems that for the half cycle during which the mass moves from left to right, the equation of the motion can be this. For left to right, like this, the motion from left to right. Okay. And let's assume the solution for this equation. This is the equation for left to right motion. Let's assume the solution with x of t is equals to a1 cos omega nt plus a2 sine omega nt minus mu n over k. So applying this into this equation, that it will be the solution. Omega n is the natural frequency, which is radical k over n. Another case is when x is positive and dx over dt is negative. That means still it is moving towards to left to right, but accelerating to back. And dx for half cycle during which mass moves from right to left. The motion still is from right to left, but with negative velocity. Means it is still in the right side. So for that case, the equation of motion becomes this part. Previously it was negative, but now it is positive, plus. So what we can get is this equation. Okay. So let's consider another solution for this case. A3 cos omega nt plus A4 sine omega nt plus, because it is plus here, mu n plus k. Here it is minus, so we used like this. So the term mu n over k appearing in equation is a constant representing the virtual displacement of the spring under the force mu n, or the force friction force actually, if it were applied as a static force. So this graph indicates that the way how amplitude is decreased from every half cycle, how it decreases, even within every quarter cycle, how it reduces, it shows. So we can see it later. So the motion of mass with Coulomb damping is represented as this graph. Look, equation of motion for Coulomb damping system. So now we have two equations and two different solutions. But how we can combine those two equations and the two different solutions together? For that purpose, we use some signum function. Because now we have two different situations. Moving from left to right with positive velocity and moving from left to right with negative velocity. How we can define those two terms together? That is the question behind. So that signum function for the velocity term x dot for positive and negative can easily be described with the help of this equation. So signum of x dot is equals to, it is 1, positive 1, if for x dot greater than 1. That means when x is positive, the signum x dot is equals to 1. If this is 0 for x is equals to 0, and minus 1 for x dot less than 1. For any velocity that x dot is less than 1, it is minus 1. So this is the signum function. Okay, so we combine two equations, equation number 1 and equation number 3. Equation number 1 means this one, okay, this one. That means when moving to the to left to right with positive dx dt is equal to positive. This means x dot is equals to x positive, x dot is greater than 1. Okay, in this case, and the second case, x dot is negative, x dot less than 1. Okay, so moving left to right with a negative velocity for x dot. So these both combine together to get this particular equation. Okay. Mu x dot dot plus, no, sorry, mass times acceleration, that is x dot dot plus mu mg, mg is the weight, signium x dot plus kx is equal to 0. So this the signium function is already defined here. Okay, to find solution using this procedure, let's consider initial conditions. These are the initial conditions considered. Okay, x of t is equal to 0, or is equal to x naught, and x dot of t is equal to 0 is equal to 0. This is actually the case of x dot is equal to 0 condition. Okay, so that is the system starts with 0 velocity and displacement x naught at time t is equal to 0. So applying these equations to equation number 4, what you can get is constant A3 is equal to x naught minus mu n over k. So applying that initial conditions for this equation, okay, let's substitute x naught here. X naught is equals to A3 cos omega nu t 0, cos 0 plus sine 0. So this part becomes 0 because sine 0 is 0. So x naught is equals to mu n x naught is equals to A3 plus mu n. So A3 is equals to x naught. Let's see, x of x naught. Let this x of t is equal to x naught, which is equals to A3 times cos of 0 is 1 plus this is times 0, A4 times 0 plus kn kn over mu n over k. So from here, A3, this is A3, sorry, A3 is equals to x naught minus mu n over k. Yes, that is what. And then similarly applying for x dot t, what you can get is A4 is equals to 0. Okay, so let's reapply this thing into the equation. Okay, so this is the final equation for a particular case. Another here, this solution is valid for half cycle only. It's valid only for 0 to pi over omega n only for the moving towards to right for half cycle. That means when t is equals to pi over omega n, the mass will be at its extreme left position, and the displaced from equilibrium position can be found using minus x1. Let's consider x1 as the first position. Let's see that x1. Where is x1? This is x0. X0 here. Yeah, x1 here. Okay, so we are here now. Minus x1 is equal to x of t is equal to pi over omega n. So when we substitute t is equals to pi over omega n on the equation, what will happen? X naught is mu n k cos omega n. Okay, so instead of t, pi over omega n, so omega n cancelled by omega n, we have left cos pi. That is simply this equation. We can get this equation for the first x1 in the downward direction. This minus indicates that in the downward direction, then this position. Yeah, minus x naught minus 2 mu n. This is x1, the first x1. Okay. Now, since the motion starts with displacement of x1 in half cycle, the value of x becomes minus x naught minus mu n k. The reduction in magnitude of x of t in time t is equal to pi over omega n is mu n over k. So it is reduced this amount from the total. So let's see that what it is. This is the amount reduced from, previously it was from here to here, but currently it is this equal to x naught minus mu n 2 times mu n over k. So in every half cycle, we can see this reduction, this amount of 2 mu n k reduction. Pi over omega n. This is half again. Here also 2 pi over omega n. 3 pi over omega n. So the amplitude reduced from time to time. Okay. Okay. So this is our equation. This is equation for the velocity. In the second half cycle, the mass moves from left to right is to be used. The initial conditions are the same. We use the same initial condition. Actually, the initial condition will change here. Why? Because x of t is equals to 0 for the value of x at t is equal to pi over omega n. When we apply it in the equation 6 is this equation, okay, mu n over k. So by applying this thing, these values, t is equal to pi over omega n in the equation 6, what you can get is minus x naught minus 2 mu n over k. From that, we can find a1. A1 is equals to x naught minus 3 mu n k. This is A1 value. And at the same time, x dot of t is equal to 0, which is equal to value of x dot t. X dot t means this equation, okay, at t is equal to pi over omega n. In this in equation 6. Okay, let's substitute this to this equation. Then what we can get is A2 is equals to 0. So we have A1, A2 0. We have A3, A4 0 there. So now the solution becomes x naught minus 3 mu n over k because we apply this equation into A1, x naught minus 3 mu n over k. Okay, so cos omega n t minus mu n over k. The solution is valid for, again, pi over omega n to 2 pi over omega n. Now our solution works from pi over omega n from this point to this point only. It works for this interval. The previous solution works for this interval only. Okay. So in this interval, that is half cycle. So at the end of this cycle, after t is equal to 2 pi omega n, the value of x of t is x2 is equals to x of t is equal to pi over omega n in equation 7. Equation 7 means this equation. Okay, equation number 7 is this equation. Substitute it into this equation. Finally, what we can get, x naught minus 4 omega n over k. And the x dot t is equals to, in equation number 7, what you can get, you can see. So this becomes the initial conditions for the third half cycle. These values, x2 and x dot, are the initial conditions for the third cycle. And it will continue like that until the complete decay will occur. Okay, and the procedure can be continued until the motion stops or it ceases. The motion stops when xn less than or equal to mu n over k. Since the restoring force exerted by the spring kx will then less than the friction force mu n. Therefore, the number of cycles represented with r that elapses before the motion ceases is given by x naught minus r mu n over k less than or equal to mu n over k. That implies r should be greater than or equal to x naught minus mu n over k over 2 mu n over k. This is the point where complete motion or the oscillation will cease. So Coulomb fraction is a rule used to describe energy dissipation caused by Rabi friction. So let's take one example on this part, because in order to understand more clearly, examples are used. Find the free vibration response of spring mass, spring mass system subjected to Coulomb damping for the following initial conditions. X naught is equal to 0.5 meter, x dot is equal to 0, mass 10 kilogram, k is equals to 200 newton per meter, and damping value 0.5. That is very high damping value. Most of the time we know friction coefficient is about 0.3 or something like that, but here it is 0.5. So the equation of motion is this equation, as we have seen, and applying the Rank-Kutta method. That the Rank-Kutta method is one of an important method of solving ordinary differential equations in our mathematical calculation. So that we applied the Rank-Kutta method here. So x1 is, let x1 is equals to x of t, then x2 is equal to x1 dot. If x2 is equal to x1 dot, that implies x of t dot. Let's consider this as function of function f1 of x1, x2. And x2 dot is equals to x2 x dot dot t. Why? Because that x2 dot is equal to x1 dot dot, which implies x of t dot. So which is equals to let's apply this equation on this main equation. X dot dot means if we bring this this equation here from x dot dot is equals to let's bring mass to here, mu times n means mg, so mass is already done, mu g times, this is minus actually because bringing back to the equation. So now signamium SGN of x dot. This x dot means it is x2 rather than x dot itself. Yes, because this x dot means x2. X2. Okay, minus q over m. Q over m times x means what? X means x1. This x of t is equal to x1. So x1. So they are combined like this. X2 is equals to x dot dot of t, which is equal to mu g signamium of x2 minus k m over x1, which is considered a function f2 to f2 of x1 and x2. Here x1 and x2 both are z. Okay. Here also x2 and x1 are available. That's why. So equation 2 and equation 3 can be expressed in mathematical notation. We can express them as x dot is equal to f of x, okay, where x is equal to x1 of t, x2 of t, and f is equals to f1 of x1, x2, f2 of x1, x2, and x of t, which is the initial condition, is equals to x1 of 0 and x2 of 0. So these are the definitions of this equation. So implementing these equations into the MATLAB program, we directly plot the graph. Okay? We implement the above equations, these equations into MATLAB program. And the MATLAB code will give us defining some x terms, other different terms. Finally, g is this value. And finally, what we can get is this graph. This is the graph. Okay, so you can consider this as an equilibrium position. Okay, equilibrium position. Okay, this is the MATLAB plot of the particular question. Note that the following characteristics of system with Coulomb damping. One, the equation of motion is nonlinear with Coulomb damping. But in the case of viscous damping, it is linear. The equation of motion is linear in the case of viscous damping, but in the case of Coulomb damping, it is nonlinear. So that's why we applied rank-Kutta method for the nonlinear equations, because nonlinear equations can easily be solved with the help of rank-Kutta method. For this, we can see one best example in the next case. The natural frequency of system is unchanged with the addition of Coulomb damping. Reduces with the viscous, because in the case of viscous damping, the natural frequency reduces with viscous damping. Why? Because omega n is equals to, no, omega d is equals to, in the viscous damping, we call it as damped viscous damping, damped by natural frequency. So that is omega n times 1 minus zeta square. So, so it is reducing with the damping. As the damping increase, okay, this omega n decrease. Again, the motion of is periodic with Coulomb damping. Okay, while non-periodic with viscous damping. There, in the viscous damping, we have observed that a logarithmic decrement of amplitude. But here, a linear decrement, that is mu n over k amount reduction in every cycle. What we observe from here is mu n over k reduction in every quarter cycle. In one full cycle from here to here, we can observe 4 mu n over k reduction. The reduction from here, if we consider it for one complete cycle, 0 to 2 pi over n, we can see x naught minus 4 mu n over k. Here it is x naught. Here it is x naught minus mu n over k. That means about 4 mu n over k amount reduction, linearly reducing the amplitude. But there the reduction is logarithmic. That e the power of some value. Okay, so because of that, viscous damping is not like that. The system comes to rest after some times with Coulomb damping. But in the case of free vibration, it will go vibrate, remain. Actually, not in the viscous damping, it will go vibrate, but takes long time. The amplitude reduces linearly with Coulomb damping, but in the case of viscous damping, it is reduced exponentially. So these are the conditions. In each successive cycle, amplitude of motion is reduced by the amount mu 4 mu n over k. In each successive, in 4 full cycle, the amplitude of reduction is 4 mu n over k. So the amplitude at the end of any 2 consecutive cycles are represented with this equation. Okay. As the amplitude is reduced by an amount mu n over 4 mu n over k in one cycle, in terms of 2 pi omega n, the slope of the envelope, straight line shows dotted in figure. And that means the line which inclined line which touches all the graphs, which is represented by 4 mu n over k, the whole over 2 pi over omega n. That is the slope. Means this is slope. If I draw this line like this, the slope of this line, okay, slope is this, delta y over delta x, or you can say this slope. Sorry. So that is the slope, which is equal to minus. This minus implies the slope is from declining slope. Okay, from right to left, declining slope. So which implies minus. Okay, 2 mu n omega n over pi k. If the final position of the mass is usually displaced from equilibrium x naught position and represents the parameter displacement in which the friction force is load. So that is all about the what you call this Coulomb damping. So in the next we'll see structural or hysteretic damping condition. So this is enough for today. Thank you for attending for following the lecture. Thank you.